Special products or expansions. So some products are worth remembering because they follow a certain pattern and give you shortcuts in expanding your algebraic expressions. So we look first in these three special products. That is a square of sum, square of difference, and a difference of two squares. Basically, the first two formulas give you a shortcut how to expand this sort of expression. So if you have sum or difference squared, it expands as first term squared plus, if it's sum, or minus if it's difference, to product of the both terms plus square of the second term. So it's pretty easy to remember, and it's useful if you can recognize it from and use it from left to right and from right to left. And another nice product which you need to remember is a difference of two squares. Very, very useful. So basically, if you multiply sum and difference of the same terms, this is how this expansion ends up. That is square of the first term minus whatever minus here, the square of the second term. So you save time on collecting like terms and etc. So we should be able to recognize these three formulas in examples. For example, expand 3x minus 2 squared. So okay, does it look anything like here? Yes, that's the difference. This is my first term, that's my second term. So I'm applying this formula, square of the difference, which says square of the difference is square of the first term. Yep, so I don't do simplification here yet, I'm just applying the rule. Minus double product of the first term times second term plus second term squared. So now when I applied my special product formula, I can simplify my expression. That is, so term by term, 3x squared is 3 squared, 9, x squared. So first term down, minus. So what I have here, 2 times 3 times 2 gives me 12. X, right, plus 2 squared plus 4. So that was the first example. Next, again, we have 5x plus 1 squared. That is a sum. Applying the formula which says first term squared plus double product of first term and the second term, don't forget that one, plus second term squared. And now I'm simplifying it, which gives me 5 squared, 25, x squared, that's the first term, plus 2 times 5, 10, x plus 1. So I expanded it, and once you use it for this formula all the time, it comes very easy. Now, this doesn't look like either square of the sum or a difference. However, it looks pretty much as the third formula, which says if you have difference of the same terms times sum of the same terms, that expanded as first term squared minus second term squared. And finalizing it, we have 16x squared minus 9. So these three formulas are very useful, and particularly useful if you can recognize, for example, from this form, you can go to this form, so you can factorize. I just mentioned factorization, and factorization continuing here with more examples. So why do we need to factor? factorization is an important technique of simplification of algebraic expressions. That is, at some point, if we have the same factor numerator and denominator, we can cancel it out. But first, we learned different techniques of factorization. First, it was special products. Now, technique called common factor. So basically, your aim is to present your expression as a product of some factors. So you look if there is a common factor in all terms of the given expression. For example, here we can present 9x as 3 times 3x minus 3y. So the common factor is 3. So now we do the process factorization is a process opposite to expansion of the brackets. So 3 can be taken to the bracket, outside of the bracket, and whatever left we put inside the bracket. So here we have 3x, and from this term minus y. So we presented our expression as a product. So the same we try to attempt in the next examples. Okay, so we'll look for the common factor, something which is you can see in both terms or as many terms as you have in a particular expression. So what I see straight away is 4, and both of the terms have a and both of the terms have x. So let's present both of them as 4ax, which is a common factor, times whatever left. So 8ax squared is 4ax times what? 2x, right? Okay. Next expression, next term is 4ax, don't forget, times 1. Yeah, because something will stay here within the bracket. And now we are ready to factorize. So 4ax is a common factor, goes outside of the bracket, and inside the bracket we get whatever left. So from the first term we have 2x, and from the second term we have 1, not 0, because a lot of people do this mistake. When you multiply, the remaining of the product is 1. So we factorize. Okay, now we will practice factorization using the formula difference of two squares. Remember, we had, I'll use different notation, a plus b, a minus b equals a squared minus b squared. So we're going to use this formula. Okay, see, first example is very simple. So we have x squared minus 25 or 5 squared. Okay, now we can apply formula. That would be first term plus second term times first term minus second term. Easy. So not as obvious here on the next example, but we should recognize those squares and write our terms explicitly. For example, 4x squared can be presented as 2x squared minus, okay, 9 is happened to be 3 squared. So now we can apply difference of two squares, and we know explicitly, we showed explicitly what are the terms. It's 2x and 3. Applying this formula, that would be 2x plus second term, which is 3, and 2x minus second term. And that our factorization here. Okay, next example, well, not that obvious because 20 doesn't look like complete square. Well, we can't apply difference of two squares straight away, so we try to find common factor first. So what I see that both of these terms have 5 as a common factor. So 20 is 5 times 4, and we have x squared, minus 5 times 9. And now it looks much more promising, because if we take 5, the common factor, out of the brackets, what left? 4x squared minus 9. And we know how to factorize it, because that's exactly difference of two squares, and we just did it before. So I'll just use the result above, and that would be simply 5 on 2x plus 3, 2x minus 3. Yes, so maybe we cannot apply our formula straight away, but combination of techniques will allow us to get the result. Now, the next expression, can we apply difference of two squares? Yes. It's just we have a square of some algebraic expression, and that would be our a from here. And here what we have, 9x squared is 3x squared, and that's our b. Now we wrote explicitly two terms, and we apply in this formula. Okay, that would be first term, which is y minus 4, plus the second term, which is 3x, times first term, which is y minus 4 minus 3x. That's it. Mission completed. We factorized. Well, continue our factorization examples. Here we probably will have to apply twice and basically try to factorize. Here's just try and go. For example, you could go and say, okay, I have 2x and ax as like terms, and minus 2y and minus ay. Okay, let's try to factorize those. So this should be with two lines. Okay, let's try and see what happens. So x would be common factor, that would be x. What's left? 2 plus a. Okay, done the first pair. Then minus y is a common factor, and what we have? We have again 2 plus a. Okay, that worked. So what is the common factor? 2 plus a. That's a common factor now. And we can finalize our factorization, which would be 2 plus a is a common factor. And whatever left from the first term is x, and from the second term is minus y. Obviously, this example could be done different way, and that would be your homework. Okay, factoring trinomials. In this course, we'll deal a lot with expression like this. So trinomials, basically, we have three factors: something square plus something to the power 1 and a number. So these sort of quadratic expressions. And the skill to factorize it, that is present as two linear factors, would be very important and have a lot of applications. Okay, case number 1. When we deal with trinomials where x squared have coefficient of 1, there is a very simple technique. So to factorize it, we think about two numbers such that, let's denote them a and b. Sum of these numbers will give you coefficient for x, that is x, which is 8 in our case, and their product will give us this number, 7, which doesn't have any x. Yep, so usually it works for very simple examples, and well, it's useful to know. So we easily can see that a, for example, would be 1 and b would be 7. Yeah, 7 times 1 gives us 7, and 1 plus 7 gives us 8. And in this case, factorization would be the following. So x plus 1 and x plus 7. So just let me write the general formula for trinomials. So we're considering expressions of that type. So I'm using like in general terms. So A is coefficient for x squared, B coefficient for x, and C is a free number. Let's put it this way. Okay, so let's see, can we apply the technique we just learned to the next example? Well, not from the first side, because coefficient for x squared is not 1. Yeah, so this is applicable only when coefficient for x squared is 1. Maybe we can bring it to this case, because I noticed that all three terms have 2 as a common factor. So I factorize it first, and what I get? 2. From the first term I have x squared minus 8x plus, well, 12. So I reduce this example basically to the previous one. So now I have trinomial with coefficient for x squared equals 1. Again, I think about two numbers. So I'll write here x, x, and I won't forget this 2. So I'm prepared to factorize, such that their product is 12 and their sum is minus 8. So what I can think of is that minus 6 minus 2 equals minus 8, and minus, can you see it? 6 times minus 2 equals 12. Fits. Okay, so I just put in this bracket minus 2 and minus 6. Let's check. How do you check whether or not you factorize correctly? I will go back to this form. So I'll rewrite 2 and expand those brackets and see what happens. So x times x gives me x squared. Then x times minus 6 minus 6x, and then minus 2x, 2 times x minus 2x minus 8x, and minus 2 times minus 6 is 12. So I factorized correctly. Okay, this next example won't allow us to reduce this case to the case when x squared is coefficient for x squared is just 1. In this case, we use the technique called drawing the cross and basically enumerating all possible possibilities. So first, we will think about all possible products which can produce us this coefficient for x squared. Well, fortunately, there is just one combination, is 3 and 1. 3 times 1 is 3. Okay, we're drawing the cross. Now we start enumerate all possible combinations of numbers such that their product is minus 6 and cross multiplied with 3 and 1, this sum will give us 7. So it sounds complicated, but it's much easier when I start doing this. For example, we can think of 3 and minus 2, right? So now cross multiplied. Okay, 3 times minus 2 gives me minus 6 plus 3. So does it give me 7? No, it's not equals to 7. So this doesn't fit. So I think about other combination. What about I change them places and I put minus 2 and 3. And again, do the cross multiplication. Okay, 3 times 3 gives me 9. And minus 2 times 1 gives me minus 2, gives me 7. So it fits. Hence, I completed application of this technique. So I'll have two brackets here. So that's 3 and 1. So I'll write here 3x. And here would be just x. So coefficients according to the top row. And then whatever numbers I end up fixing in my bottom row, which fit, I will put here. So that would be minus 2 and that would be plus 3. Okay, let's check whether or not we factorize correctly. That is, if we expand this expression, we have to come back to 3x squared plus 7x minus 6 equals. So I'm going back. 3x times x gives me 3x squared. So far, so good. 3x times 3 gives me plus 9x minus 2x minus 6, and that is exactly 3x squared plus 7x minus 6. Okay, and let's repeat this technique again about drawing the cross. Okay, what we start with? We start with all possible combinations, which in product gives us 4. So, for example, 2 and 2. Okay, 2 times 2 gives me 4. And then I explore all possible combinations of numbers which can give in product minus 14. There are not that many, so I enumerate all of them. If I find something which is cross-multiplied, give me 1, I'm done. If it's not, if I can't find any of them, I will move to next combination, which gives me 4, and do the same procedure again. All right, so 2 and 2. So possibly, for example, minus 7 and 2. So cross multiplication of this gives me the following: 4 minus 14. So that's not 1. So that doesn't fit. Okay, possibly I could put 7 and minus 2. Again, I get minus 4 plus 14. Again, it's not 1. And basically, this is all possible combinations, which gives me minus 14, since I have 2 and 2 on left and right. Okay, let's look at different combination which produce us 4 as a product. I want to make sure that you can see it. Okay, for example, 4 and 1. And that makes our life easy, I believe. So let's try the combination minus 7 and 2. Look what happens. 4 times 2 is 8, and minus 7 times 1 is minus 7, gives me 1. Fit. So my expansion would be the following. So draw 2 brackets and have 4x, that's coefficient here, minus 7, and, well, x times 1, x, plus 2. So that's the expansion. Let's check whether or not we did it correctly. Open the brackets. We have 4x squared plus 8x, first term multiplied on everything here, minus 7x minus 14. And finalizing, we have exactly where we start, the expression we started with. Further factorizing techniques. So another 2 useful formulas is sum and difference of cubes. So again, these are shortcuts and it's good to remember, and it just helps you to simplify expressions more efficiently. Okay, these are the formulas. So basically you had sum or difference of cubes and you reduce it to some linear factor. Linear, that is everything to the power of 1, and some, that's a mistake, that should be 2 squared, obviously, and some quadratic expression as well. Okay, let's apply these formulas to those examples. So first is pretty straightforward. So we have x cubed plus, we need to know what our second term explicitly. So 27 is 3 cubed. And now we just apply the formula. So we have sum, hence we have to use the first formula. And it gives us, so first term plus second times first term squared minus product of the terms plus second term squared, which is 9. And that completes the first example. Now, Second example. First, we have to recognize explicitly what cubes we're dealing with. Yep. So 27 is 3 cubes, as we know, minus 8 is 2 cubes. So hence, the second term can be presented as 2x cubed. And now we know what our first term, which is 3, and the second term is 2x. Applying the second formula. That says difference of the terms times first term squared, which is 9, plus, well, I won't finalize it now, product of the terms, which would be 3 times 2x, plus second term squared, and finally we'll have 3 minus 2x on 9 plus 6x plus 4x squared. Okay, final example. Again, it doesn't seem like anything doesn't have any cubes. Okay, start with common factors. So what I can see that the common factor is what? 7x squared. Let's write it explicitly. 7x to the power 5 is 7x squared times x cubed, right? And we're applying index laws here. Minus 7x squared times 1. Expanding, so now we can collect, now we can factorize. Okay, 7x squared is a common factor. What is in the brackets? X cubed minus 1, and that is difference of 2 cubes because 1 cube is 1. So we can write cubes straight away here and apply the formula. That would be 7x squared times x minus 1 times x squared plus product of x and 1, which is x plus 1.